All right, so to get started, talk about the exam a little bit. Did have our biggest curve yet on this one. It is a hard exam, so it had 10-point curve on it. That being said, we had, I think, 3 or 4 people up in A range. Those of you guys who weren't as happy with how you did and stuff like that, this is kind of how the rest of the semester is going to be with this type of exam, right? Because we're basically into metabolism now. We're doing a lot of metabolic pathways and stuff like that. So just make sure, if you need extra help, come get it. Make sure you're studying early and studying very thoroughly too, because there's, a lot of mechanisms and stuff like that as well. So make sure you're paying attention to that, learning them early, and also not just looking at them to learn them, but actually writing them down, like practicing drawing them out, stuff like that, because I know from personal experience, sometimes you can look at one of these mechanisms and go, okay, that makes sense. But then when you actually have to reproduce it, it's something else entirely. Even with the same with the structure drawing, right? My first TAing experience, for those of you guys who haven't heard this story before, the first time I TA'd in grad school was for second semester biochem, and we started off with glycolysis, and I got up there to the front of the room and was trying to draw the glycolysis pathway, go through the enzyme mechanisms, and I realized that I couldn't draw glucose. I couldn't just on the spot draw glucose. Make sure you practice drawing those things. That's the lesson I learned then. Hopefully you guys will learn it now. Yeah. All right. So we'll go through some of the questions here anyway. Some of them are fairly self-explanatory, or you can just look them up. Like number 1, it's just the names of all the intermediates. So starting with glucose, glucose 6-phosphate, fructose 6-phosphate, so on and so forth. Structure of phosphoenol pyruvate. That one, basically I gave you guys a point for the organic part of pyruvate, 1 point for the phosphate group. Next part, provide a reason why PEP is a high energy compound. 2 reasons I was looking for there, and I accepted others as well, but you absolutely had to say something about the enol state, right? The keto enol state for one of them. So basically PEP is trapped in the enol form. It will spontaneously tautomerize once the phosphate's cleaved to the keto form. So you had to say something about that. And then for the other one, I accepted basically charge repulsion, because you have actually several negative charges on PEP, depending on pH. You have increased hydration, increased resonance, all that happen when you cleave that bond. So I accepted any of those for kind of the second reason. Now on the next 2, these ones, so for your quiz on Wednesday, I just want to make sure to reiterate, since I know it's been spring break, people have forgotten what I said on Friday of last week, or 2 weeks ago. So your quiz on Wednesday, I'm going to ask you to draw one of our enzyme mechanisms from that last exam, not like one that was in the last exam, but one that you should have known for the last exam. So all the enzymes from glycolysis are fair game, right? Enzymes from fermentation are fair game. Glycogen degradation and synthesis, those ones are fair game. Pentose phosphate, those ones are fair game. So you got a lot to learn, but we're playing catch up now at this point. All right, so make sure you study those for Wednesday. Now, because of that, so Wednesday we'll likely also be starting chapter 18. I'm not going to doubly burden you with a pre-chapter 18 quiz on Wednesday. Instead, I'm going to give that to you on Friday. I am going to give you the pre-chapter 18 quiz, but it'll be kind of sort of into chapter 18 a little bit, but I'll get you the questions and stuff like that. But I want you to focus on these enzyme mechanisms for Wednesday. Right? So pyruvate decarboxylase, that's the enzyme in fermentation that's removing the carboxylate group and making acetaldehyde. So you should have had thiamine pyrophosphate involved in there. Does the attack, decarboxylation, protonate cleave. Right? Pyruvate carboxylase is one of the harder mechanisms, admittedly, in the chapter. This one's part of gluconeogenesis. Wait, that's the other pathway you need to know, sorry. This one, we start you have to load CO2 onto what's the cofactor that we use to do carboxylations. Let's get the gears going again. And remember what coenzyme we use to do carboxylations. Some of you guys have it on your paper, or no? Biotin, right? All right, so biotin is the cofactor that we use here, or you should have used. All right, so we've got to load CO2 onto biotin. And the way we do that is we use ATP to make that acetyl phosphate compound. Biotin can now bind CO2, and then CO2 can leave, and basically pyruvate can do a nucleophilic attack on it. Right? So if you need help with those, look them up in the textbook, or come find me, and I'll go through them in person with you. But all right, number 5, why is fermentation required under anaerobic conditions? So I expected you guys to say something about to regenerate NADH, or sorry, to consume NADH or regenerate NAD+, something along those lines in order for glycolysis to continue to occur. All right, number 6. All right, so get used to kind of seeing these new sorts of enzyme things. This is going to be kind of a common question type I'm going to tend to ask you guys. Where, okay, you've seen this type of reaction before, but not this exact reaction. All right, I expect you guys to be able to kind of figure out how this would work. So this one I am going to draw out for you here. All right, so what we would do with this one, so the part that is changing on the molecule is right here, right? The hydroxyl group is becoming a ketone. And we've seen this type of reaction several times during the course of the chapter. So like the enzymes you should be thinking about would be like alcohol dehydrogenase, lactate dehydrogenase, right? This enzyme's basically going to follow that same pattern, right? And so what happened in those enzyme mechanisms is, I'm going to draw the structure. Well, I guess I'll put on the proton here. So you got to remember there's a proton on there, right? All right. Now, what ends up happening is that we need to have a hydride leave. So that's how we oxidize alcohols to ketones. So we have a hydride leave, and electrons from the oxygen collapse down to form the double bond. So we always have to have a base to deprotonate the alcohol. All right, that frees up those electrons to collapse down. So we can have now these electrons collapse down like so. And then that kicks off the hydride to the NAD ring. Oh, sorry. So it does attack at the top. Then we do our little ring around the rosy with the electrons like that, right? All right, so this is what you should have had for that mechanism. So you got to start recognizing patterns. This is, in metabolism, this is semi-similar to organic chemistry, right? So you've seen a mechanism before with one molecule. You draw the same mechanism with a different molecule. All right, number 7 then. When glycogen is fully degraded, the products are glucose 1-phosphate and glucose. Where do both products come from? Can somebody help me out with that? Remember, so first one should be fairly easy, hopefully. Glucose 1-phosphate comes from which enzyme? Glycogen phosphorylase, right? That's our main enzyme that breaks down glycogen. So it produces glucose 1-phosphate as a product. Now, where is the glucose coming from? There's one other enzyme that produces glucose as part of its mechanism. Anyone remember? Debranching enzyme, right? So debranching enzyme, it moves basically all but one of the sugars in the branch over to another chain. Then there's still that one glucose unit, if you recall, right? And it cleaves that off, just producing free glucose. Right? So that's how we end up with the glucose component of the breakdown. All right, number 8. Most people did really well on this one. All right, epinephrine binding to receptors of cells leads to increased production of cyclic AMP, activation, protein kinase A, increased phosphorylation and glycogen synthase, and glycogen synthase then. So if you want to, with this sort of question, like if you can't remember these three here, right, that's okay. Like it's not ideal, obviously. You're responsible for knowing that sort of stuff. But this last one, right, you guys should all be able to just think about this one, right? So epinephrine is adrenaline, right? Now, for the physiological response to adrenaline, do we want to be storing sugar? No, right? All right, so we do not want to be storing sugar. So do we want glycogen synthase turned on or off? Off, right? So this part at least, so remember that you can kind of rationalize your way through these sorts of questions sometimes like that. So, the first three, yeah, you would have had to memorize those to a certain extent. But the last one, you should be able to just kind of figure out by thinking about what adrenaline is and what it's actually going to do inside of the cell. All right, number 9, this is one that a lot of people struggle with, and I understand it's kind of an offshoot part of gluconeogenesis that we talked about briefly, but it's very important that you understand it. So PFK2 and FBPase2, all right, these are not the same as the enzymes in glycolysis, right? The enzymes in glycolysis and gluconeogenesis are PFK1 and FBPase1. All right, so now PFK2 and FBPase2, these make and break down fructose 2,6-bisphosphate. Right. So PFK2 is responsible for making that compound. FBPase2 is responsible for removing the phosphate off to give us fructose 6-phosphate back. So let me draw this slightly differently here. So basically the reaction they're doing is going from fructose 6-phosphate forward and backward to fructose 2,6-bisphosphate. Now, these guys over here, the PFK1 and FBPase1, they're the enzymes in glycolysis, and they're going from fructose 6-phosphate to fructose 1,6-bisphosphate. All right, so this part here is in glycolysis. All right, now the whole reason for these two enzymes and this particular compound here, all right, is to regulate glycolysis. So this compound here is basically serving as an allosteric regulator for PFK1 and FBPase1. Right? It's coming up and regulating those guys. Right. Now, anyone remember fructose 2,6-bisphosphate? I said that this is kind of a mimic of what other compound. You can kind of think of it this way. Oh, I like to think of it as a mimic of glucose. Actually, is what one of the things that I kind of so in terms of like how it's going to relate to its response. So like if we have lots of sugar in general, we're going to have lots of fructose 2,6-bisphosphate. All right, so if we have lots of sugar, do we want to be making more sugar with gluconeogenesis or breaking down sugar to maintain homeostasis? Break down, right? We want to break it down because we have too much. So which of these two enzymes here, PFK1 or FBPase1, which one of these do we expect to be upregulated by fructose 2,6-bisphosphate? So which one is in glycolysis? Anyone remember? So remember, if we have a lot of this compound here, fructose 2,6, this is a sign we have lots of sugar in general. Right? Which one of these two enzymes up here is in glycolysis? PFK1, right? So fructose 2,6-bisphosphate upregulates PFK1 and downregulates or inhibits FBPase1. So it's an activator, basically. So turn on, there's a little plus sign there. So it turns on PFK1 and it turns off FBPase1. But its levels are actually controlled by these other two enzymes. So that's the whole idea here for number 9. So you had to say something about PFK2, FBPase2 making fructose 2,6-bisphosphate, and then say something along the lines of it activating PFK1 and inhibiting FBPase1, or activating glycolysis, inhibiting gluconeogenesis, something along those lines. That's what I was looking for there. All right, number 10, this is one everyone did pretty well on. Why can't gluconeogenesis simply carry out the pyruvate kinase, PFK, and hexokinase reactions in reverse? Because their delta Gs are negative, they're a reversible enzyme, something along those lines there. All right, explain why reactions that are slow in metabolism tend to have negative delta G values. All right, so for this particular question, you needed to basically explain through. So I think there's one other type of answer I gave credit for with this as well. But what I was looking for basically was for you guys to explain through this particular equation. And instead of having Q here, I'm actually going to add in the so actually write out the Q part. So we have products on top, reactants on bottom. So if a reaction is slow, you'll tend to have a lot of reactants laying around because the reactants are going to build up because the reaction is not occurring very fast. You also tend to have a low level of products because, again, the enzyme's not making products very quickly. So basically, this fraction in here is going to, since you have a smaller numerator and a big denominator, that fraction is going to be very, very small, all right, which means the natural log of a small fraction is going to end up being negative. All right, so this part over here is basically going to reduce delta G. That's what I wanted you guys to explain to me for number 11. All right, number 12. So using the tables and equations at the end of the exam, calculate the following. So delta G of hexokinase producing glucose 6-phosphate. So I'm going to have to scroll up a little bit further. All right, so you should have come to this particular table here. And so I said glucose turning into glucose 6-phosphate using hexokinase. So we need this particular delta G right here. All right, so that's, you got to remember what this table is showing us here. These are free energies of hydrolysis. So what that means is this is the energy, this number here is the energy of glucose 6-phosphate plus water, giving us glucose. It's the energy of hydrolyzing the phosphate off is what it is, plus our inorganic phosphate. Now, for hexokinase, is this a reaction that hexokinase carries out? No. What am I missing from the hexokinase reaction? ATP also, right? ATP gets consumed during the hexokinase reaction. And so we've also got to incorporate this reaction. All right, so we've got, I'll write that one up here. So ATP plus water, giving us ADP and phosphate. Now, I have these two delta G values now. I have the minus 30.5 for ATP, minus 13.8 for glucose 6-phosphate. Now, basically what I want to do is I want to add these two reaction equations together to give myself the hexokinase reaction. Now, hexokinase, if you recall, is taking ATP, which is already on the reactant side, and glucose, which is unfortunately on the product side right now, and reacting them together to give us our products. So I'll kind of draw a squiggle around glucose 6-phosphate and ADP. So in this top equation here, the reactants and products are on the correct side. On the bottom, they need to basically switch sides. We need to reverse this reaction. So we can keep the top energy the way it is. So it is still minus 30.5 kilojoules per mole because the ATP reaction, we didn't have to flip it or anything. The glucose 6-phosphate reaction, though, we did have to flip it around. And so what we do is we just simply change the sign. So we add 13.8 to this. And what does that give you? Sorry, not feeling like doing math this morning. A negative 16.7 kilojoules per mole. That's what you should have gotten for the answer there. All right. The next equation, or next question, sorry. So our other calculation question is calculate delta G0 for alcohol dehydrogenase producing ethanol. So for the alcohol, can somebody help me out with what the actual reaction is that alcohol dehydrogenase carries out? Everyone remember? Yeah. Acetaldehyde plus NADH giving us ethanol plus NAD plus. All right, so this is a reaction that this question is asking about. So you had to be able to kind of figure that out first, otherwise you'd struggle to get the rest correct. All right, so we're talking here about a redox reaction. Anytime we are involving NAD, NADH, you should immediately recognize that as a redox reaction. So in order to figure out delta G's of redox reactions, we have to use our electron potentials. And so we're going to go to a different chart, this one down here. Right. And we basically need to find the two different half reactions in this chart. So one of the things that we're doing is taking acetaldehyde, converting it to ethanol. Well, that's right here. Here's the E0 value for it. All right, the other process that we were doing was taking NAD plus and converting, or actually we're taking NADH, converting it to NAD. So we're doing this reaction here, but in reverse. All right, so just like with the delta G's of hydrolysis, right, we're basically going to add these two together, but if we have to flip a reaction, we're just simply going to flip the sign on E0 here. So we can leave the negative 0.197 alone, right, because that reaction is written in the correct direction already. But this one down here, we have to flip-flop it, so we're going to add 0.315. All right, and this is going to end up giving us our E0 value of the reaction, which it should have gotten 0.118 volts, positive 0.118. Now, we're still not done with the question yet. So this is step one of solving this type of question. All right, because the question is asking for delta G. All right, well, we have an E0 value here. We have to be able to relate that E0 value to delta G, and the equation that we use to do that is delta G equals negative NFE. All right, well, in this particular case, N, we look at these reaction equations to figure out how many electrons are being transferred. All right, and we've got 2 there, so N is 2. All right, F was given to you, it's 96,485. And our E0 value is right there. Just figure that out. So if you multiply that all together, you should get a delta G value of approximately negative 22,770 joules per mole. All right. So let's wrap up the exam. We got a few more questions here. All right, draw a ketone reacting with a lysine side chain to form a shift space. Let's go ahead and draw that real quick for you guys. So we have a ketone group. Doesn't matter what you have on the ends. Just had to be a carbon double bond oxygen. Right, you got a point just for drawing me a ketone. Then a lysine side chain. Right. I was actually fine just with like an NH lyse, but if you drew more of it, that's great. But you had to draw something along these lines here. Now, the way this reaction occurs, it occurs in 2 different steps. So first of all, what we're trying to make, just to review for you guys, sometimes this can maybe help you with figuring out your direction you need to go. So it shifts base, if you recall. is a carbon with a double bound nitrogen, and that nitrogen has a positive charge. So if you remember what this is, what your end product's supposed to look like, sorry, let me erase that dot, there we go. That can help drive what you're trying to do reaction-wise. So we obviously need to have this nitrogen here attack the carbon at some point, and we need to have the oxygen fall off. Right? Those are the two goals that we have here. So let's go ahead and do that. Let's do a nucleophilic attack, push the electrons up, and protonate it. All right, so we end up now at our intermediate stage. Sorry, let me write that as a lysine. All right, we end up with this sort of a structure here. Actually, let me redo these protons because I'm going to need to show what's happening with them next. So there we go. All right, so we end up with this sort of state, right? Well, we now need to make a double bond between the carbon and nitrogen, and we need to get that oxygen fully off. So let's have the nitrogen do another nucleophilic attack. Well, that sounds like a great idea. The problem is the nitrogen has no lone pairs of electrons, so what should I do to that nitrogen first? Anyone? Deprotonate it, right? So we'll use a base. Let's have a base here. Deprotonate nitrogen. That frees up some electrons to do our nucleophilic attack and kick off the hydroxide. Okay. And now we're here at our shift space. So you had to have those two steps there. All right, number 14, explain what the role of shift space plays in transalkylase. So basically you had to say something about stabilizing the negative charge to aid in the cleavage of it. Aid in the cleavage of the carbon chain, something along those lines there. All right, the last one, number 15. So this one was kind of the outside the box thinking question here. All right. Consumption of high fructose corn syrup is closely associated with obesity. Your lab partner tells you that one reason for this is that fructose can bypass a key metabolic control step when metabolized in the liver. All right. Are they correct? Explain. All right. Well, let's work through this real quick. So fructose inside the liver, basically it gets turned into two molecules of GAP basically that re-enter glycolysis. There's a couple steps in the middle here. There's like, I think 2 steps in the middle in there. But I'm not going to worry about that right this second. All right. But if we're basically able to take fructose and get immediately down to glyceraldehyde 3-phosphate. All right, there are 2 major steps of glycolysis that we've bypassed. Anyone know what they are? And there's one in particular that's particularly bad to bypass. What are the regulatory steps of glycolysis? Phosphofructokinase, that's the one I'm looking for, but what are the other 2 real quick? Hexokinase and pyruvate kinase, right? All right, so hexokinase is our first step, glucose to glucose 6-phosphate. So we are bypassing that one here because we're never using glucose. Phosphofructokinase is the enzyme that takes fructose and makes fructose 1,6-bisphosphate. In this upper portion here, we never actually do that reaction, right? So basically, this enzyme is bypassing both hexokinase and phosphofructokinase, which are the steps that allow our bodies to regulate glycolysis. Now, all right, so basically, when we consume lots of fructose is able to be metabolized by our body through glycolysis, essentially without control. Right? Now, so that's one of the things that you should have realized with this. Now, we have to think this through all the way to the end, though, because this is asking about, high fructose corn syrup being associated with obesity. Now, all right, so I'm talking right now about, okay, we can metabolize sugar really, really well, right? But can we get fat from metabolizing sugar really well? Anyone help me out with that? I think this part was missing from most people's stuff, but I kind of, for like the complete holistic explanation I was looking for. What happened? What's the very end of glycolysis? And think about like our metabolism chapter. What are our two major metabolic metabolites that link, for instance, sugar metabolism to fat metabolism? You know, remember acetyl-CoA, right? Where is acetyl-CoA located? Bottom of glycolysis, right? So basically, fructose is able to be turned into acetyl-CoA, which then gets turned into fat in our body, essentially without control. Right? So this is part of the reason why you see a lot of dietitians and stuff like that, nutritionists, really kind of blasting high fructose corn syrup, is because even if you were to consume the same amount of glucose for sugar, that would actually be better for you, because glucose can be regulated, so the production of acetyl-CoA is going to be lessened. You're going to tend to become less obese consuming high levels of glucose as opposed to high levels of fructose. So that is it for the exam. Anyone have any questions at all about any of the stuff I covered? All right.